Swayam Prabha. Digital India. Educated India.
Hello, welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT KANPUR. So we are into the 6th week of our lectures on Nonlinear and Adaptive Control. And in this week, we have already started looking at our first adaptive control problem. So before we move on, of course, we want to remind ourselves that the algorithms that we develop and the systems that we analyze with the tools we've learned are meant to develop and design algorithms that drive systems such as the spacecraft that you see in the background, and autonomous. Right? So that's sort of what we are targeting to do with the tools that we learn in this course. All right. So a little bit more detail on what we have been looking at. Yeah. So we started with our first sort of adaptive control problem, and this was a first order scalar system. So it's a first order differential equation describing the system. And of course, it's scalar valued states. And therefore, we are dealing with a first order scalar system where the unknowns appear linearly and are assumed to be constant. Yeah. So, how we went about this is that we wanted to sort of, the control objective was basically to track a desired trajectory R of t. Yeah. And therefore, we designed an error variable. So this is the sort of standard step. We design an error variable E of t, all right, which is essentially just x minus r. And we also then wrote the dynamics for this error variable. All right, since we know the dynamics for the state, writing the dynamics for the error variable is rather easy. Right? Then the first step was to do a control design for the case when the parameter theta star is assumed to be known. Right? And we did that by choosing some kind of a nice target system. We talked about the properties of a target system, that it should be viable, that is, it has to have some kind of a matching with the original system. And secondly, it has to ensure that the error has nice asymptotically stable properties. So this is the target system we choose in this case, and it satisfies both our requirements. In order to get to this target system, we require a control which looks like this. Yeah. And it's evident that the parameter, of course, appears in this control because we essentially cancel the nonlinearity. Yeah. And once we are able to do this in the known parameter case, we choose a radially unbounded Lyapunov function, and we compute the derivative, which turns out to be minus k e square, which is asymptotically stable, and all the nice things, and so on and so forth. Yeah, excellent. Now, beyond this, it was obvious that just by using the Lyapunov theorems, error goes to 0 and all the nice jazz. Yeah. Now, how do we deal with the uncertain or the unknown parameter case is the application of the certainty equivalence principle, which essentially said that you retain the same structure of the controller, but you change the, you replace the true parameter value, which is unknown to you, by its estimate. Okay, and this estimate is going to be designed subsequently. So with this altered controller, we get a altered error dynamics, yeah, which contains now the parameter error, which is denoted as theta tilde. Right? And so what's the idea? The idea is that we use a Lyapunov function to come up with the theta hat dot. We use a Lyapunov candidate to come up with the theta hat dot dynamics. How do we do that? we take the earlier Lyapunov candidate we had, and we add to it simply a quadratic term in the parameter error. It is scaled by this gamma factor, which is essentially called the adaptation gain. You will see why, because it appears in the adaptation law, right? And we just then start simply taking the derivative. We of course don't know what is theta hat dot, we are yet to prescribe it, but we know what is E dot, and that is substituted in here. And it so happens, magically, like I said, well, actually not magically, but by construction, that you have theta tilde appearing in both these terms, and therefore theta tilde can be taken out common. Yeah, and so you have this sort of an equation, and what do? You simply ensure that this quantity is zero. All right. Why do you have to ensure this quantity is zero? Because it is a mixed term. Like this term is a nice negative quadratic term. There is no sign definiteness in this term, which means I cannot, you know, guarantee it's positive or negative definite. In fact, we want negative definite things in the v dot, right? Therefore, the best thing we can do is to sort of cancel this and make this zero go away, right? Then, so this is what we choose. You choose theta hat dot from here so that this goes away, and this is essentially your adaptation law. And you see that this gamma appears here, which is essentially what we call the adaptation gain, because changing gamma will change how fast the adaptation happens. So if I make gamma really small, then the adaptation is really fast, and so on and so on. The important thing to remember, and a mistake that a lot of folks make, is that your update law or your control law cannot depend on theta tilde, because theta tilde is unknown. Yeah, theta tilde is unknown because it contains theta star, right? Therefore, theta tilde cannot appear in the control law or the update law, because if it does, then your controller or your update law is not implementable, and this is of course no longer adaptive control, then it's actually not something that can be used at all, right? Great. So then what do? That was the sort of final stage. We got this v dot is minus ke squared. What we notice is that the v dot we get in the adaptive case, that is in the unknown parameter case, is the same as the v dot we end up with in the known parameter case. But there are two differences. Well, there is one major difference. Is that in the known case, there's no theta tilde squared, which is obvious because there is no parameter error. Parameter was assumed to be known. But in the unknown case, there is in fact a theta tilde squared term in the v, which means in a known case, v dot was negative definite because there was in fact only one state. Right? But in this case, we have actually introduced an additional state theta tilde because we have to, otherwise we don't know how to update our parameter. So the fact that we get the same v dot does not mean we also get negative definiteness. In this case, we get only negative semi-definiteness. Why? Because we had emphasized this many times during our Lyapunov analysis sections, and also now that v dot, if any function does not contain some of the states of the system, then it cannot be definite. It can only be semi-definite, right? And that's what this is, only negative semi-definite, and therefore by using the Lyapunov theorems, you can only claim that the E and theta tilde states are uniformly stable at 0, 0. So you can only claim uniform stability and nothing more. So this is critical. Yeah. So this is where we were until last time, and then we will see now today how we go forward from here and in fact claim all the properties we need, because we need asymptotic stability, not uniform stability. Uniform stability is not enough because it just says that if you start small, you remain small. If you start with small errors, remain with small errors and things like that. But that's not enough. We want the errors to actually go to 0. We want to do actual tracking. Yeah, that is what is the whole point of this adaptive control theory. All right, so how do we do that? So that's what we see in today's lecture. Let me mark it. It's lecture 6.3. All right. So the first thing to remember is that what we do with typically mixed terms, that is the terms that we cannot cancel. Sorry, there's the terms that cannot be made negative definite is we try to cancel them, and that's what we did when we chose our adaptation law. As simple as that. Okay, so now what do? We only get uniform stability, so we carry out the signal chasing and Barbalat's lemma analysis. Now remember that we already saw a sample of signal chasing in Barbalat's lemma when you're looking at the analysis part of the syllabus, and so we should already have a little bit of an idea of what's about to come. Yeah, and so we start. We have, if you remember, I had spoken at that time extensively about there being these very, very standard steps. Yeah, these are steps that I had mentioned at that time that all of you just need to master. Yeah, and I mean, in fact, just memorize so that you never sort of change the sequence of the steps. So once you just follow these steps, the same set of steps work in almost all cases. In fact, in a lot of these new research articles on adaptive control, the authors don't even mention these steps anymore. Yeah, because it's so standard that they, once you have a V dot, they pretty much conclude whatever is expected. Okay, so they expect that the reader already can sort of follow these steps on their own. Right? Great. So this is the signal chasing analysis. So remember where we are. I will again write out some key points. So V was 1/2 E squared plus 1/2 gamma tilde squared. Alright. And V dot came out to be, and so this is of course positive definite, radial unbounded and all the nice things. And V dot came out to be minus K E squared, which is negative semi-definite. Okay, so this is what V and V dot were. So this is where we start. So the first thing we claim is that V is lower bounded and non-increasing. So that's obvious. So V is lower bounded because it's strictly positive definite. And it's non-increasing because V dot is less than equal to 0. The derivative is less than equal to 0 of a function of time. Then of course the function cannot increase over time. Right? It can do anything but not increase over time. Right? It's a non-increasing function. And we know from these two properties that there exists the limit as t goes to infinity for V of t. Right? So limit t goes to infinity V of t exists and is finite. And what do? We denote this with V infinity. We are going to use this V infinity in our subsequent calculations. Okay, so that's step 1. Okay, remember, you should just compare these steps with what we did. I believe we did this for the spring mass damper sort of example using the Barbalat's lemma. Should compare these steps, and you should be able to see that these steps are rather standard. In fact, they're the same, almost the same steps that we did even then. Okay, and in the same sequence also. Yeah. All right. So now the second point is, since V is finite. Now, why is V finite? So V0 is of course finite. It doesn't make sense if you already started at infinite state or infinite parameter error or something like that. Just not realistic. So V0 is finite. And what do I know? I know that V of t less than equal to V0. Okay. So notice that I am sort of using this funny notation where now I'm earlier V was a function of E and theta tilde dot. I mean, although I've not written it, it was something like V is a function of E theta tilde. But now suddenly I'm writing V as a function of time. Okay, so please do not get confused. Whenever I say V of t, it's actually defined as V E of t and theta tilde t. Okay, and what is E of t theta tilde t? These are solutions. Okay, these are solution trajectories. So remember, so there is a lot of things that are happening here that are sort of implicit, which I'm not saying, but that should occur to you and that should be very clear to you. The first thing is when I write V of t, that is V as a function of time, I mean that I'm now plugging in the value of E, that I'm plugging in the solutions here. Okay, not just E and theta tilde as some variables, but the solutions. Now remember, though I've written this as E of t and theta tilde of t, these implicitly depend on E0 and theta tilde 0. So E0 is here and theta tilde 0 is here. In fact, both are in both of them. Right? So these are actually also dependent on E0 and theta tilde 0. Yeah. Please do not forget this. Yeah. So whatever we get as an outcome of this analysis is not uniform with respect to initial conditions. Yeah. Because once you choose an initial condition, you get some outcome. Okay. The good thing is we don't have to actually specify what initial condition, because for any initial condition, all this entire analysis will go through. Okay. We're not that worried, but still it should be there at the back of your mind that this expression of V of t that I write here so nonchalantly actually contains the initial condition, because V of t is obtained by writing the solution of E and theta tilde as a function of time. Okay, that's how you get V of t, and that's how you compute V dot, right? Otherwise, there's no question of computing a time derivative if there is no time. This how do I compute a time derivative? This and so this when we use this notation, yeah, you remember that this is basically just the directional derivative along the dynamics. Yeah, and this is exactly consistent with V being a function of time. If I took dV by dt, this is exactly how I would do it. Yeah, I would take dV by dE, E dot, dV by d theta tilde, E theta tilde dot. This is exactly how I would. Yeah, therefore the two definitions are consistent. Yeah, so therefore when I take derivative with respect to time, this is actually a valid sort of operation. Okay? So therefore V of t has a lot of hidden meaning. Yeah. So please remember this. Yeah. Excellent. So now that we know that V dot is less than equal to 0, therefore V of t is less than equal to V0. What does it mean? It means that V of t is also finite because V0 is finite. And if V of t is finite, it means that E of t and theta tilde of t are also finite. And what do we know about signals that are finite? We know that they belong to class infinity, L infinity. Okay. If a signal is finite for all time, then it belongs to class L infinity because the infinity norm is finite. Yeah, because it's just the supremum. If E of t and theta tilde of t are finite for all t, then their supremum norm, that is the L infinity norm, also has to be finite. Okay, right. Now, the next thing that we do is we integrate both sides of this equation. Right. So, yeah, and it's claimed here that E is L2 from integrating both sides of the derivative of the V dot equation. Okay. Now, how do we get that? Here, it's not sort of explained. How do we get that? Let's try to integrate this. So, if I integrate, say, V dot dt 0 to t, and this is less than equal to minus k integral 0 to t e squared tau d tau. Okay. Now this is actually equal to dv. Okay, so this will be v0 to vt. Yeah, and this is dv. Okay, and this is less than equal to minus k again 0 to t e squared tau d tau. All right. So what can I say now? I can say from here, if I take limit as t goes to infinity on both sides, what do I get? I get that v infinity minus v0 is equal to minus k 0 to t e squared. Sorry, not this is 0 to infinity E squared tau theta, which means that 0 to infinity E squared tau theta is equal to V0 minus V infinity divided by K. Okay. Okay. And what is this? This is just the square of the infinity norm, right? So this is basically just equal to the 2 norms squared. Yeah, and we have just proved that it is finite. So that's what we are saying, that by integrating both sides, I can get that the 2 norm is of E is finite, which means that E is an L2 signal. Okay, which means that E is an L2 signal. That's what we have proved. Okay, that's what we have proved, that the 2 norm squared is a finite quantity, therefore 2 norm itself is a finite, L2 norm is a finite quantity, and if a signal has a finite L2 norm, then the signal is said to belong to L2. Okay, that's what we said. And now we can immediately, well, I mean, are we done? No, we are not yet done. We are not yet done. There's a step in between here. Okay, there's a step in between. And what is that? This in between step, I'm going to mark it as 3.5. And what is it? I can also claim that E dot belongs to L infinity. How? How? What is E dot? E dot is, let's see. Let's try to look at what is E dot. E dot is just let's see, sorry. E dot is this quantity. Yeah. So it's minus KE plus theta tilde F. So let's just copy it here. So I'm going to do this bigger. E dot is minus KE plus theta tilde F xt. Okay. So if I assume F xt bounded for bounded x and for all t. Okay, if I make this assumption, I already know that E theta tilde are bounded. Yeah. So I know that E is bounded, therefore KE is bounded. I know theta tilde is bounded. Also, if E is bounded, then X has to be bounded. Yeah, because right. So EL infinity also implies XL infinity. Why? Because E is just X minus R, and R is a bounded smooth signal, right? Therefore, if E is bounded, X is also bounded. If X is bounded, I'm assuming that this function is bounded for bounded X and all, then for all time. Yeah. So therefore, this entire right hand side is bounded. Okay, that is what is E dot is an infinity. So, okay. And then we can directly use the corollary of the Barbalat's lemma. I really hope all of you remember. If not, you should revise it, go back and revise it. I'm not going to state, well, I will state it. Essentially, the Barbalat corollary says that if a signal is L infinity and LP for some t, and if the derivative of the signal, that is E dot, is L infinity, then the signal goes to 0 as t goes to. Okay, and that's what we have for E. For E, we can claim that E is both L2 and L infinity. So P is 2, and I can also claim that E dot is L infinity. Okay, and therefore I have that E goes to 0 as T goes to infinity. Now notice we already have the uniform stability result. Yeah, that the fact that, you know, E and theta tilde are uniformly stable at the origin because of the standard Lyapunov theorems. But now we also can claim that E converges to 0 as t goes to infinity. Okay? And this is very good for us, right? Why? Because we had an unknown parameter, right? And what did we do? We designed an adaptive controller. Why? Because we had the control, we had a controller, and we also had an update law. And with these two elements, I can claim that the tracking error actually goes to 0 as t goes to infinity and also remains uniformly stable, which is rather nice. Yeah, I can't claim asymptotic stability of the entire system like I would have loved to, but I still can claim something rather nice, that the tracking error remains stable and converges to 0 or the origin as t goes to infinity. Yeah, which means that I get my exact tracking in spite of an unknown parameter. So this is the power of adaptive control. I want you to sort of absorb it. Yeah. So I've not said anything about theta tilde yet. Yeah. Not said anything about the theta tilde. So look at what happens. Okay, let's look at what happens. Yeah. So, but the important thing to note is that the tracking error goes to 0 in spite of there being unknown parameters. Okay. So now we want to know if the unknown parameters converge to true value or not. Yeah. How do we do that? So we say we know that E dot is integrable since E goes to 0 as t goes to infinity. So how do we claim that? E dot integrability means that if I do this, yeah, this should be finite. And this is because I will essentially get limit as t goes to infinity E of t minus E0 here, which is just minus 0 because this limit is going to 0. You just proved that. Okay, so E dot is an integrable signal. So that's the first claim here. Second is you can compute E double dot to verify that E double dot is also bounded. Okay, how do we do that? It's not too difficult, right? What is E double dot? We already saw what is E dot. Is this guy? Okay, so I just have to take the derivative of that. Yeah, so this is E double dot is equal to minus K E dot. I'm not writing K E dot explicitly yet. Plus theta tilde dot F plus theta tilde F dot. I've removed the arguments from F. Okay, so I'm not going to write K E dot. So this is minus because I know E dot is already bounded. So minus K E dot plus theta tilde dot, which is, what is theta tilde dot? Theta tilde dot is 1 over gamma EF. Yeah, theta tilde dot is in fact negative of 1 over gamma, 1 over gamma EF times F, so it's EF squared plus theta tilde F dot. So now what do I know? I know that E dot is bounded. We already proved it. E dot is bounded. We already proved. Okay. Then we know that E and F are bounded. F is bounded by our assumption. E is bounded by the Lyapunov analysis. Now if I further assume again something on F dot, assume F dot bounded for bounded X and all time. Okay, see, we make a similar assumption on F dot as we did on F. Okay, then what can I claim? I can claim that this entire quantity E double dot is also bounded. Okay, so that's what we do. We can verify very easily that E double dot is also bounded. Now, one of the results that we had looked at said that if E dot is uniformly, if E dot is bound, E double dot is bounded, that is the derivative of a signal is bounded, then the signal itself is uniformly continuous. That's what we claim here. And so this is then by the original Babolat's lemma. What does the original Babolat's lemma say? It says if a signal is integrable and if it is uniformly continuous, then it goes to 0 as t goes to infinity. So from that, we know that E dot was integrable and we know that E dot was uniformly continuous. Yeah, therefore E dot goes to 0 as t goes to infinity. So we have not just proved that E goes to 0 as t goes to infinity, we also proved that its derivative goes to 0 as t goes to infinity. Yeah, we did this very carefully, yeah, without resorting to our usual mistakes or the pitfalls in adaptive control or pitfalls in nonlinear analysis, where if a function goes to 0 or a function goes to a constant, we assume its derivative goes to 0 and things like that. No, we did this very carefully, okay, and formally. Okay, so E dot goes to 0 as t goes to infinity. Now, what was E dot? Yeah, what was E dot? E dot was this thing. So if I know that the left hand side goes to 0 as t goes to infinity, I know this guy goes to 0 as t goes to infinity. Yeah, then what am I left with? I know that this product also has to go to 0 as t goes to infinity. Okay? And that's what I write here. But this doesn't mean anything about the convergence of theta 10. And that is what is standard in adaptive. Alright, excellent. So what did we look at today? We sort of tried to complete our analysis for this first order scalar system. And we are sort of at the end of this analysis. Yeah. Essentially, we required the use of Babolat's lemma and signal chasing in order to complete this analysis. Right? And what we are able to show is that in spite of a parameter error, the tracking error goes to 0. Yeah, so therefore we can do exact tracking. So if it's a robot, we can exactly track a trajectory. Yeah, but we cannot guarantee that the parameter converges to its true value. We can only show that something like a theta tilde times f goes to 0, which doesn't mean necessarily that the parameter goes to 0. Alright, excellent. So this is where we stop today, and we look at more details of this kind of problems in the subsequent sessions. Thank you.